Hello friends, welcome to Wisdom Training's Hadoop Developer course. In this video we'll be talking about Hadoop architecture. So let's begin with Hadoop architecture. So in the Hadoop architecture, the very first thing that we're going to talk about is Hadoop ecosystem. So if you see here the logos of different platforms and different projects that are available in Hadoop ecosystem, you see Hadoop in the middle and you see different projects surrounding Hadoop. You have your Hive, you have HBase, Oozie, Mahat, Flume, Scoop and Pig. So all these projects, right, combined with Hadoop forms the Hadoop ecosystem. So we'll be talking about each one of them in brief here. So we have spoken, or we have taken up the these platforms or projects in detail in the coming parts of the module. But here we'll be talking briefly about all of these, right? And we'll also see how do we classify these projects, right? So let's see the classification first. Okay, so coming to this slide, you have your Hadoop, which has two main core components, that is HDFS and mapreduce, that we'll be talking in detail in this video. You have your HBase, Hive and Pig as warehouse database. You have your Scoop and Flume, which is used to push the data into HDFS from various resources. You have Oozie, which is a workflow scheduler wherein you can schedule your jobs, and you have Mahat, which is used to develop machine learning algorithms and applications. Okay, so let's talk more about Hive. Okay, so Hive, if I talk about Hive here, hold on. So I have Hive here, right? So Hive is basically a platform which is used to develop SQL-like scripts for MapReduce. So there are people who are not familiar with the programming, but they are very good in SQL, right? So for those people, or for those developers, SQL developers, they have designed a platform wherein they just need to write simple queries, and at the back end the MapReduce functionality of the application would run. Okay, so for make them familiar, or to make them enable to work on Hadoop, a platform was designed, which was designed by Facebook, which is called as Hive. Okay, we'll be talking in detail about this project in the coming parts of in the coming modules of this course, right? So Hive is a SQL-like scripts for MapReduce, right? So it is mainly used for processing the structured data. So mainly used for processing the structured data. So Hive is mainly used for processing structured data, and it is used to develop SQL-like scripts for MapReduce. Alright, then you have something called as Pig, which is also similar to Hive, but it's a kind of abstraction to MapReduce. You don't have to be good at coding. Abstraction 2 actually. Okay, it has its own language, which is called as Pig Latin, wherein you write the scripts in Pig Latin, and at the back end the same MapReduce task is performed. Alright, so it also has a Pig engine which understands the Pig Latin script and do the functionality and performs the job. It basically converts the Pig Latin script into MapReduce functionality. Alright, so then you have Hive and Pig. If we talk about HBase, it is a column-oriented database that we'll be talking in detail. Just for now, see it as column-oriented database, which is a part of NoSQL database, that is not only SQL. Okay, then you have Flume, which is used to push the streaming data into HDFS. Alright, then you have Scoop, whose literal meaning is sequel to Hadoop, which is used to push the data from SQL or SQL to Hadoop, right? So if you have your SQL server here, and here is my HDFS, so if you deploy in between, hold on, let's say this is my Scoop, and here is my SQL or SQL Server, and I have my Hadoop or HDFS. So Scoop will help us transfer the data from SQL to Hadoop and vice versa as well. Alright, so from Hadoop to SQL. So this is a Scoop platform that we'll be talking in the coming parts of our course. Alright, then you have something called as Mahat. It is used to develop machine learning applications using Hadoop as or HDFS as storage. Then you have Uzi, which is a workflow scheduler. Alright, wherein you can design your jobs and in which particular order that jobs will run, so you can do that in your Uzi. So these are few of the projects that I've listed here, and I've written few things about them, which forms the Hadoop ecosystem. Alright, now let's go to the slide as well. So Hive is a distributed data warehouse, manages data stored in HDFS and provides a query based language based on SQL. Okay, if you talk about Pig, it's a data flow language and execution environment for exploring very large data sets. Pig runs on HDFS and mapreduce clusters. Okay, then you have Scoop, which transfers the data between structured datasets and HDFS. And if I talk about HBase, it's a distributed column oriented database. Then you have Flume, service for efficiently collecting, aggregating and moving large amounts of log data, okay, from different sources. So here it's given as log data. Uzi is service for running and scheduling workflow of Hadoop jobs, and Mahat is a project to build an environment for quickly creating scalable, performant machine learning applications. Right now, our main focus here will be regarding the core components of Hadoop. So the core components of Hadoop are HDFS and mapreduce. So HDFS is Hadoop distributed file system, so which is a storage component, and it provides a distributed storage. You have different nodes wherein your data gets stored. Okay, and you have mapreduce, which is a computational framework which splits the task into multiple nodes, and parallel processing is done on different nodes that are available. So let us talk firstly about HDFS and what all things are there in HDFS. We'll talk in detail in this video. Alright, so if I talk about HDFS, you have three software daemons here. The very first one is the name node, then you have a secondary name node, and then you have data nodes. Okay, let me just go back to the notepad and let me just annotate it for you. So you have three software daemons here. The very first one is your name node. The second goes secondary name node, and the third one is data node. Alright, so this Hadoop or HDFS architecture is a master slave architecture. Alright, wherein you have your one master and multiple slaves. So the master here is your name node, and the slave here is data nodes. So as per this stated information here, what I can draw here on the basis of the written part, that I must have multiple data nodes. Let's say I have these many data nodes, and I have a bigger one, name node. So this is D2, D3, D4 and D5. That is data node 1, 2, 3, 4 and 5. So I have 5 data nodes and 1 name node. As the architecture suggests, from the name master slave. So the master will be controlling the slaves, right? So here this name node will be controlling all the data nodes. Alright, so this is a master slave architecture, and this is HDFS architecture here. Alright, so you have name node, you have multiple data nodes. Okay, so what is the functionality of name node and what is the functionality of data node, that we need to discuss in detail right here in this video or in this module. Alright, so let's start with a name node, and then we'll be talking about data node and secondary name node. Okay, now so I'll again draw the picture here. Okay, so I have this name node now. Let's say I want to write I have a file, let's say abc.txt. So what Hadoop architecture does, it converts, or it splits the file into different blocks. Let's say block 1, block 2, block 3 and 4. So this is my B1 here, B2 here, B3 here and B4 here. Alright, so I have 4 blocks, that is I have converted my text file, or the file that I want to place it on HDFS, into 4 blocks. Alright, so these 4 blocks have to go on my data node. So the actual storage is being done on the data nodes. Name node takes care of the namespace of the the data nodes. Alright, so what do you mean by namespace? I'll tell you here. Let's say I have data nodes here, 4 data nodes. Okay, so I'm gonna give it a name as D1, D2, D3 and D4. So now let's say my B1 is getting stored on D1, that is block 1 is getting stored on data node 1. My B2 is getting stored on D3, that is data node 3, and my B3 is getting stored on data node 4, and my block 4 is getting stored on data node 2, right? That is, if you see, if I mark the arrows, B1 to D1, then you have B2 to D3, okay, then you have B3 to D4, and then you have B4 to D2. So my all blocks are getting stored in this way. So this parameters, or this information about the storage of the blocks, can be considered to be as namespace. Plus the name node also, you can say this as a file structure and directory structure information that is present on name node. Okay, the actual storage is being done on the data nodes, but what is getting stored on which location, which block is getting stored on which location, how many files are there, what space is empty on data nodes, that all the records of, or the information about the cluster is kept on the name node. Alright, you can also say it has the information regarding list of the files that are stored on the cluster, on the data nodes. It also have the list of the blocks of the files. Alright, then it can also have location of the blocks, where the blocks are getting stored. Then it must have the ownership details and permission details. It can also have the storage capacity of, or storage capacity or information of each data node. So all this kind of namespace plus the metadata, that is data regarding the data. So data regarding the files which are kept on data nodes is taken care by the name node. So this is the major functionality of the name node. Name node decides which block will go to which data node. Alright, and it keeps a track of all the information, or all the blocks information, all the files information, all the storage information of the cluster. So name node is acting as a master here, and which decides that which data node will go to which block will go to which data node. Alright, so this was regarding the name node. Now coming to the data node. So as we already discussed, data node is actual storage location. You can have as many data nodes based on the volume of the data that is being generated in your cluster. So you can have multiple data nodes, right? So it's an actual storage. So actual storage is being done on data nodes. So if we talk about the creation, deletion, and so the creation and deletion of the blocks, that is being taken care on data nodes. Alright, now coming to your secondary name node. Okay, so before I talk about the secondary name node, I also need to talk a little bit more about name nodes functionality. I'm coming back to name node here. So we discussed about name node here, but I have missed a thing here. So name node, it maintains two files in its drive, that is called as fs image and edit logs. Okay, so what is fs image? It is it contains the namespace information, and if you talk about the edit logs, it tracks the changes that is being done to anything that is being done, changes in the cluster or the metadata. So it tracks the changes to the metadata. So what kind of changes I'm talking about here? So for example, there is some new block creation, there is some new files are getting written. So all that changes that are being taken care to, that are being happening in the cluster will get recorded in the edit logs. Alright, now when this edit logs, they keep on updating, but fs image doesn't. So fs image only loads into the system when you restart. So it gets loaded into name node once the system restarts, and the edit logs, the previous edit logs are truncated, and fs image, the previous fs image is getting discarded. Okay, and the new fs image gets loaded into the directory. Okay, so what do I mean by this? That it maintains two files, right? fs image and edit logs. Edit logs tracks the changes to the metadata, but fs image gets loaded into the name node's main directory, memory only once the system restarts. Okay, so once the system restarts, fs image gets loaded into the memory, and the earlier newly created fs image is loaded into memory, and the older one, so see, there are changes in the edit logs, right? So edit logs keep these changes to the fs image, and then new fs image is printed, and the older one is discarded, and edit logs are truncated. So this is the process, but restarts do not happen so often in the production environment. So this restarts do not happen so often, so it's a hardly done affair. So in order to avoid this stuff, you have something called as name node, which comes to the rescue of name node. Okay, so the secondary name node comes to the rescue of name node. So what it does is, hold on, now, so I'm trying here with the secondary name node, and this is my name node. Okay, so here comes my secondary name node, and this is my main name node. Alright, so what secondary name node does is it keeps on bugging or asking name node for the edit logs, and name node it sends the edit logs, that is updated edit logs, because edit logs keep on updating as soon as there are changes in the metadata that record is published in the edit logs. So it sends the edit logs to secondary name node. Now the secondary name node has its own FS image file, and name node also has its FS image file. Now what a secondary name node does is, now it has taken the edit logs from the name node. What it does is it updates its own FS image. Okay, now it has updated its own FS image, and next step what it does is, at the regular intervals of time, it keeps on copying its own FS image to name node. Okay, copies it's the FS image to name node. Now the name node has the latest changes. Okay, so the name node has the latest changes without restarting the cluster or without restarting the name node. So secondary name node helps helps to keep the FS image up to date. Okay, it avoids the restart conditions, and if there are any changes in the edit logs that are as soon as there are any changes, these are replicated in the FS image of secondary name node, then FS image which is present on the secondary name node is getting copied on the name node. So in this way name node gets updated FS image, okay, which has all the information regarding the changes that are being done at regular intervals of time. Alright, so this is the functionality of secondary name node. We talked about name node, we talked about secondary name node, and we also spoke about data nodes. Right, now let us go back to the slides and see if something has been missed. So if we talk about the HDFS, it's a distributed file system that provides high throughput access to data. It provides a limited interface for managing the file system to allow it to scale and provide high throughput. Okay, another thing that I missed here is, so once you split the data, so let's say here you have a file here abc.txt, and you split the data into different blocks. So there is something called as replication factor. Okay, so for example, I have certain blocks here. This is my B1, B2, and I have B3, B4, and B5. So each block will have a replication factor. So default replication factor is 3. That is, each block will be replicated on 3 data nodes. In case of a failure, right, in case of a failure, other 2 will be available. So if one data node fails, other 2 will be available, and our job will keep on running. Alright, so you have replication factor as 3. So B1 will be replicated on 3 data nodes. Similarly, B2 will be replicated on 3 data nodes, and same goes for B3, and so on. So each block will get replicated on 3 data nodes. So if one node fails, the other 2 will be alive. Okay, so if we talk about name node and data node communication also here, before going back to the slides, let me just talk about here only. So you have your name node, you have your data nodes here. Okay, there is a certain kind of communication that exists between name node and data nodes. Let me just write which is my name node. So this is my name node here, and you have data nodes. Okay, this is data node D2, this is data node D3. Each data node keeps on sending the heartbeat or a signal or acknowledgement. You can call it as heartbeat to tell name node that it is alive. Okay, so if there is no heartbeat, okay, so let's say it is a heartbeat here, it has sent that it is alive, and if there is no heartbeat, so what name node will do is whatever blocks were present on D2, it has all the information, right? Name node has all the information regarding each block and each files and each block storage location. So what it will do is it will replicate the D2 data node, right? So now D2 is not sending any heartbeat to name node, so now it knows that this D2 has failed, so this is no more alive, no longer working, right? So what name node will do is it will create a replica of D2 onto D3, whatever node will be available. So I'm assuming that D3 is available, it has free storage available or free space available, so it will replicate whole of the D2 onto D3, right? So this replication take place here. So it replicates the D2 on D3. Alright, so whatever data was present onto D2, it will replicate the same stuff on D3 by fetching the data from other nodes where the data, the same data was present where of the D2. Alright, so this is about the data node and name node communication. And we also spoke about replication factor, wherein each block has a certain replication factor, and the default replication factor for each block is 3. That is, each block gets stored on 3 data nodes. So if there is a failure of one node of one of the nodes, the other 2 are alive and can be the data can be retrieved from them. Alright, now coming back to the slides here. So a file consists of many blocks. Larger blocks of 128 MB, uses the commodity hardware that we discussed in our previous video, right? If you talk about the nomenclature, you have set of machines running HDFS and mapreduce that are called as Hadoop cluster, and you have individual machines that can be called as nodes. So a cluster can have as few as 1 nodes and as many as thousands of nodes. Okay, we talked about 3 different daemons: name node, secondary name node, and data node. Hold on, yeah. Okay, now talking about the HDFS architecture, we already spoke about that, and we also saw the replication as well. So if, as you see here, hadoop.txt, which is divided into 3 blocks, that is block A, block B, and block C, and each block is replicated on all the data nodes. That is, A you can see on all the data nodes, B also you can see on all the data nodes, and C also you can see on all the data nodes. So here I have only 3 data nodes, and replication factor is 3. Therefore you see them in a same manner, same order. Okay, now coming to certain points on HDFS, it's a block structured file. You have default replication factor as 3, and default block size, if it's a Hadoop 1.x and above till 2, the block size of default block size is 64 MB, and if it's Hadoop 2.0 and above, it's 128 MB. Alright, we've already spoken about the name node. It breaks the larger file into smaller blocks, right? And it manages the file system namespace in the file called as fsimage. It uses edit logs to record every transaction. So there is single node name node per cluster that we already talked about because it's a master, right? Now coming to the data nodes, multiple data nodes per cluster, thousands of data nodes for one name node. It sends a heartbeat message to the name node to ensure connectivity between the two. Alright, this is the name node and data node communication. And then you have secondary name node, we already talked about. So if a name node if a name node fails, secondary name node can be configured manually to bring up the class. So this point was missing. So if certain point of time name node goes down, you can manually bring a secondary name node up, and it can perform as name node, right? It cannot be replaced by name node if it fails, so doesn't record any real-time changes in the HDFS metadata. Okay, so we saw this. You have name node and secondary name node. It queries for edit logs at regular intervals of time, then updates the FS image with edit logs, and copy the updated FS image back to the name node to avoid the restarts. Alright, so now coming to anatomy of file read. So when you're reading a file from HDFS, there are certain functions that are called. Alright, so HDFS client, what it does is, okay, it will open, it will call an open function to DFS. Then what DFS will do is, it will ask the name node to get the block location where that file is present. So name node will return the locations of the blocks where the where the file is present or the blocks are present. Then DFS, it will create an FS data input stream for HDFS client, wherein a read function will be called repeatedly till the time all the blocks are read. So once all the blocks are read, the close function is called, and the connection is closed, and the file is ultimately read. So I repeat, HDFS client, it calls the open function to DFS. DFS then asks name node to give the locations of the blocks of the file, and once you have the blocks of location of the blocks of the file, it creates FS data input stream. Then HDFS client calls read function and reads the blocks from respective data nodes wherever the data blocks are present. Okay, now coming to your file write part, you have your HDFS client. Okay, it calls a create function to DFS, that is distributed file system, and then DFS, it asks the name node that it wants to write the name node, it wants to write a file onto the data nodes, right? So then the name node, it allows and it checks what all it gives the the list of the data nodes, what all are available, on what all data nodes the space is available, and it creates the FS data output stream. In case of file read, it was FS data input stream. In case of file write, it is FS data output stream. Okay, then here the file is split into different blocks at this location. So when the file is split into different blocks, there is an internal queue which is called as data queue, where the the file or the blocks are stored temporarily. Then you have a data streamer which consumes the data queue one by one. Okay, and it creates a pipeline. See, for example, the name node has given the locations that this data node D1, D2 and D3 are available for write. So what it'll do is, data streamer will create a pipeline and it will write the data or the block onto first node, then forwards that to second node. It copies on data node 1 and then forwards it to second node, copies it there, and then goes to third node and then copy it there. And there is something called as acknowledgement pipe as well, where their data block is present. So once all the data nodes confirms that it has got the packet or it has got the block is removed from the acknowledgement pipeline and the close function is called. Alright, so you have create function at the time of at the very first time, which is called to DFS, and then DFS calls name node for the list of data nodes. Okay, on what all that has to be written or the file has to be written. Then it creates a FS data output stream which converts the file into different blocks and puts it into an internal queue which is called as data queue, and there is something called as data streamer which will consume the data queue, and data streamer will also connect to the name node on the list of the data nodes, and then will write it in the pipeline to the data nodes, that is copies it on the first data node, then forwards the same data to the second data node on which it has to be replicated, and same goes for the third. And once all the data nodes acknowledges, the acknowledge pipeline is the block is removed from the acknowledge pipeline and the close function is called. Alright, so this was all about anatomy of file write. So there is another important concept that exists in Hadoop that is called as a rack awareness, so which is a data replicating policy or a strategy so which is taken care when you're writing the data onto your Hadoop. Okay, so what it does is it's basically done to improve the network traffics while reading or writing the HDFS files. So the name node chooses the closest data nodes which are on the same rack or nearby racks to read and write. So what a rack is, let me just tell it to you here. So if you say in this diagram you have 10 data nodes, so first 5 are considered to be as rack 1, the other 5 are said to be in rack 2. Okay, so when you have your data, for example you have abc.txt and you have divided into different blocks, that is b1, b2 and b3. Let's say I'm writing b1 onto my HDFS. So where b1 will go to data node 2, okay, and it will be copied onto the rack 1, okay, and the second replication will be on rack 2. It will not be on the rack 1, okay, it will be on the rack 2, and the third replication can be on either on rack 2 or on rack 1. So this is basically done if the rack goes down, the other rack is available. Okay, so other rack is available for pushing the data or doing the same job, or which is having the same data. Okay, so if one this complete, let's say I am saying that complete rack 1 goes down and you have rack 2 which is alive, and you can fetch the data out of this place. Alright, okay, so this is a very important concept which is taken care in Hadoop, which is called as rack awareness. Alright, so we have discussed about Hadoop ecosystem, right? So we have talked about Hadoop different platforms and different projects that exist in Hadoop ecosystem. You have HBase, you have Hive, Pig, you have Scoop, Flume, Mahout and Uzi. Then we talked about Hadoop ecosystem in briefly, right? Then you have Hadoop core components. We have discussed in this video about the HDFS core components, which is your name node, secondary name node and data nodes. That is 3 software demos: name node, secondary name node and data nodes. We talked about Hadoop architecture. How does that work? It's a master slave architecture wherein you have one master and multiple slaves. So you have one name node and multiple data nodes where the data is actually present. If you see here, you have Hadoop.txt, which is divided into 3 blocks, and each block is present on each of the data nodes. That is, replication factor is 3. So default replication factor in Hadoop is 3 here. Certain points of HDFS, you have 64 MB block size in Hadoop 1.0 and above till 2, and all the versions which are Hadoop 2.0, there's default replication factor has been increased to 128 MB. That is, each block will be of 128 MB. So Hadoop is better for bigger files which are bigger in size than 128 MB even. Alright, you have name node, data node, name node and data node communication, and we saw about this FS image updation and edit logs at regular intervals, anatomy of file read, file write and rack awareness. Alright, thanks.